Hello everyone. So today, welcome to lecture number 11, and today we are going to interpret Schrodinger equation first, and we will move on to some deeper insight of the Schrodinger equation in some simple systems. So let's start with the equation that we left in our last class. So here we finished actually. So we derived this equation, Schrodinger equation, in this form. And the question is, so once again, this is for what? Okay. So of course, this is for a particle, and the particle can be anything. So we can think of that the particle can be electron. But for a particle that follows the quantum mechanics, that means the physics of quantum mechanics, of course, and that is moving in one dimensional. Okay, so here we have only one dimension, which is x. So moving in one dimension but under a potential field ux. So under the field means force field ux. So that's why its potential energy is ux. So remember that the particle is not free. Okay, so it is under some restraining force, and the restraining force is expressed in terms of its potential energy ux. So but the particle may or may not have kinetic energy, that we don't know, because here we have assumed that some vague term of kinetic energy. So we can say that the kinetic energy is unknown, and of course also the u of x so far is vague, because we did not describe what kind of potential force is it. Okay, so whether it is a simple harmonic force or some electrostatic force or anything, we did not describe it. So therefore psi x, the solution, okay, if we solve the Schrodinger equation, we will get the solutions as psi x. We would also get it in a vague form, okay, because we don't know the terms here, so we cannot exactly find the exact nature of this psi x. But one final word to strengthen our understanding. So what does that equation mean? So this equation means, so this is representing a particle which is following quantum mechanics, and since quantum mechanical particles have wave particle duality, so that particle can be represented as a wave, and the particle is under a force field u, potential energy ux, kinetic energy unknown, and since the particle is representing a wave as well, so the amplitude function of that wave is represented by ux, which is independent of time and which is only dependent on the position of the particle. So depending on x, its potential energy would vary as well as its amplitude function would vary. Okay, so this is the correct way to understand and interpret this, the Schrodinger equation that we have just derived in a time independent manner right from the classical physics of vibration of a one-dimensional string. All right, so now let's move on to the next part, that is the Schrodinger equation can be interpreted or can be formulated as an eigenvalue problem. So what is an eigenvalue problem? So let's take a look at that. So as I mentioned, the Schrodinger equation can be expressed as an eigenvalue problem. So the question is, what is an eigenvalue problem? So before we proceed, we have to first have to make ourselves familiar with certain terms. The terms are eigenvalue, okay, eigenvalue equation, and there are two terms, operation and operator. Okay, so we will come to eigenvalue or eigenvalue equation later, and let's first start with these two terms, operation and operator. So let's imagine that we have a function, okay, y is equal to fx. All right, and suppose we take a derivative of y, the simple first derivative, okay, with respect to x, dy dx, then we can write is that ddx of fx. Okay, so now the moment we take the derivative, so we call that we have done an operation. So we have performed an operation on y to get some value of fx. So now fx has been changed. So here before it was fx, and here it is the first derivative of fx. So this part ddx, okay, so that part may be called is an operator, because an operator operates on a function and gives you some outcome. So the same thing can be represented as, suppose we have a function, suppose y, okay, and our operator is suppose g, okay, so g is my operator. So if g gets operated on y, then we may find another function, okay, so we can call that function simply say f, okay, and we can get a function f of y. All right, so this way we can actually represent. So here we can take in the sign f, but instead of f you can take anything else. Okay, so you can take this thing phi. Okay, it doesn't matter. Okay, so g is an operator. Now how to make a differentiation, how to make a distinction between an operator and a function, because in order to make a symbol looks like operator, we can use this sign g. Okay, so then this sign makes that symbol as represented as an operator. So like we can again write like this, suppose a is an operator, okay, so a operates on a function f of x and is equal to, then we get a function g of x. Okay, so here we have a operator and this is the operation, and we get g of x. So what operator can be of two types. Okay, so one can be a linear operator or a non-linear operator. Okay, so what is a linear operator? So linear operator means suppose this operator a is working on these two, okay, two functions f1x plus f2x, then as an outcome we can write individually this thing. All right, so that means the left hand side should be equal to the right hand side. So the addition of these two functions, if we take the additions first and then we do the operation, it should be equal to the individual operation. So if a operates on f1x and then a operates on f2x and then we take the summation, so both left and right side should be equal, then such type of operator is called a linear operator. And what is a non-linear operator? Non-linear operator means simply these two things won't be equal. So can you give me an example of a non-linear operator? Okay, so non-linear operator we can take as a square operator. Okay, so what is a square operator? So square operator, simply you just take any quantity and square it up. For example, you take x plus y and the operation is whole square. Okay, So x plus y whole square is not is equal to x square plus y square. Okay, so this is a non-linear operator. Okay, so and another example of a non-linear operator is the square root. Okay, so now we have a very brief idea about a linear operator and a non-linear operator. All right, so now we would come to the value of the concept of eigenvalue or eigenvalue equation. Okay, so let's erase this board and continue. Okay, so let's start with an example, a simple example. Say we can write an operation A is getting operated on a function of x, and it gives me a constant value A plus another function gx. Okay, means A multiplied by that function. So for example, we can think that this operator A may be ddx, all right, and my fx could be x square, all right. So whenever I have ddx of x square, I should be having 2x, all right. So now my x becomes gx, which is a function, another function. So previously it was x square fx, and now this is g of x. And then we have a constant term here. Before, previously it was not there, so now it came, it appeared. So we can equate that thing with a constant value a, all right. So with that kind of operation, we can say that we are having a value, a constant value appearing after we make our operation on a certain function, and here we are getting a different function. So here definitely g of x is not equal to the original function. Okay, but the question is, what if suppose my fx is e to the power ax, all right. Then if we do the same thing, so if we take the first derivative of e to the power ax, we get a of e to the power ax, and here we can also write that thing as operator a operating on fx. Here we get the value constant a, and what is e to the power ax? It is fx itself, all right. So here we have a very special relationship. Okay, so here whatever the function we get after the operation, it was exactly the previous function, so we get the function back after applying our operator. Now in quantum mechanics, such type of equation is called an eigenvalue equation, all right. And of course this is the operator, and then the function that actually fulfills this condition is called an eigenfunction. Okay, and that value, the constant that appears actually after you get back the function, that constant is called an eigenvalue. And this condition, exactly where it happens, then we call it that the system has achieved an eigenstate, or the system is in eigenstate. So whenever a system is in eigenstate, we can express any corresponding or any related equation like this. So some operator operating on a function is equal to some constant value, and we get the function back, all right. So now let's get back to our original Schrodinger equation that we have just derived in our previous lecture. So can we represent that as an eigenvalue equation? So let's check it out. Okay, so now we see we are back to our Schrodinger equation that we just derived earlier. So look at this equation carefully. You see, we can write the same equation in terms of this. So as if the double derivative with respect to x, taking it as an operator, and also the u of x, taking it as an operator, if it operates on psi x, you see we are getting the function back with some constant value e. So here you see this whole operation here can be denoted as an operator. So mind that here we have the double derivative or double differentiation operator. So let me tell you that this double derivative, okay, means the differentiation or the integration. Oh, these differentiation and integration operators are linear, okay, and therefore we do not have any problem to represent these two operation, this plus this, as a whole one single operator. Now how does this ux operates? We understand that this is a double derivative, so you have to take differentiation 2 times. Here this ux simply operates as a multiplication, so its function is to get multiplied with ux. Okay, so it works as a multiplication operator. So in quantum mechanics, this operator we represent and we call this operator as h and represented like this, and this is called a Hamiltonian operator. Okay, and the same equation can be represented as h operating on psi and giving me e of psi, or in other words h psi x is equal to e psi x. So this is also known as an alternate statement of Schrodinger's time independent equation for a particle for a particle that may or may not have any potential energy, because okay, let me tell you why. So what is a Hamiltonian operator? So Hamiltonian operator is basically the energy operator. Why it is energy operator? Because this part is known as the kinetic energy operator. Okay, because this represents the kinetic energy and this part represents the potential energy. So u of x represents the potential energy operator, and this part minus h cross square 2m multiplied by d2 dx2 is represented by, it represents a kinetic energy operator, and we know that the total energy is equal to the kinetic energy plus potential energy. So the Hamiltonian operator is represented by a total energy operator, or the reverse, a total energy operator is represented by a Hamiltonian operator. All right, so before we go further, then we can arrive at one inference, that is, yes, the Schrodinger equation for a particle moving in one dimension under a potential field ux can be represented as a eigenvalue equation. So this is an eigenvalue equation. So this is my operator. So what is my eigenfunction? Psi x now becomes my eigenfunction and E is my eigenvalue. Alright, so if we know psi x by solving this, and then immediately we know the energy of the system because we can operate h on psi x. So this is the operation. If we can know the if we can do the operation, immediately this would give me E of psi x. So with the constant value that we get here, E would become the eigenvalue, and we can easily solve the energy of the system. So later on we will frequently apply this h psi is equal to E psi equation on many systems, including the hydrogen atom. Now before we go further, so let me tell you one more thing, that the operator can be imaginary. Okay, example I will come to the second. So this is our first observation, and second observation, that in quantum mechanics we would be dealing with only the linear operators. Okay, why? Because all the linear quantum mechanical quantities or linear quantum mechanical uh, properties can be represented by only linear operator. For example, so let me erase the board and let's come back to this. So as I have mentioned earlier that all the quantum mechanical entities that we deal with, those are represented by linear operators. So that means for an example we can say, so momentum, okay, let's start with kinetic energy. So kinetic energy, the classical value is p square divided by 2m, or in other words we represent it by half mv square. So how the operator stands for? So the operator stands for p square divided by 2m. Okay, so the p cap represents the operator. And for potential energy, u of x, so here the operator stands for u. All right, position x, so the operator x cap. So this means simply that these are multiplicative operators. And momentum, okay, so classically we can represent it by p, and but the quantum mechanical operator is represented by p cap, but the value of p cap is minus I h cross del x. If it is px, means if it is represented in one dimension px, so it is minus I h cross del x. And similarly, we can think about the kinetic energy operator as px square, or then px square cap by 2m. Now you see all the operators I have written in the right hand side, those are all linear operators. So in other words, all the real quantum mechanical entities can be represented by operators which are linear. Okay, so now quickly we will try to take a look at that how a kinetic energy operator p square by 2m can be verified by squaring the momentum operator. So let's just quickly take a look over here. Okay, so now once again I have written that this is the momentum px, operator symbol px cap, and the operation is minus ih cross del x. So remember, this is imaginary. I told you that operator can be imaginary, even it represents a real quantity momentum, but the corresponding operator can be imaginary. We will later realize why the negative sign is there. In fact, we will prove it later. So, or we can represent it as also ddx, because this is in one dimension, so no other partial derivative is involved. Okay, so the point is, now we would think about the kinetic energy operator. So it is represented as px square by 2m. So this is the kinetic energy, the expression. This is the quantity in classical physics, px square by 2m. Now the operator symbol would be px cap square divided by 2m. So I want to prove that, so to prove that this is the px square, means this is the operator for the momentum px. So I want to prove that this whole square is actually nothing but the px square. All right, so how we can prove that? So of course we have to whole square this px, so therefore we can actually take that ddx, okay, multiplied by minus h cross square ddx. So you see we'll get a real value here. How? So minus I multiplied by minus I. All right, so it becomes I square, means 1, so, and then h cross square, and then we have d2 dx2. All right, so for d2 dx2 you can remember h cross square d2 dx2. So here this is the value of basically pxs square. So if we just divide it by 2m, so px square right here, if we just divide it by 2m, so we get back the kinetic energy operator. Okay, so therefore it makes sense. So we have now some idea about the momentum operator. So now we can have the idea of the kinetic energy operator. So now we can very well once again realize the true significance of the Hamiltonian operator H. So it is the kinetic energy operator, okay, by 2m plus the potential energy operator. And of course you can see the Hamiltonian operator is a linear operator because again it is representing a real quantity in classical physics, which is the total energy. All right, so we remember that the Hamiltonian operator is nothing but the linear summation of kinetic energy operator and the potential energy operator. All right, so now we have some idea about the basics of the Schrodinger equation, the Hamiltonian operator, eigenvalue, eigenfunction, eigenstate. All right, so now we are ready to apply the Schrodinger equation to solve some simple problem. Okay, so let's continue. All right. So we start again with the same Schrodinger equation. So once again, this is the Schrodinger equation for a particle moving in one dimension and which is under the potential field Ux. So now the question is it a Schrodinger equation of a free particle moving in one dimension X? The simple answer is no. Why not? Because since here the particle is under that potential field, or since as long as this particle has a potential energy, the particle cannot be considered free because it is under some restraining force. Okay, so the definition of a free particle is one and only way where its potential energy Ux is 0. Okay, so for a free particle we can rewrite this equation as minus h cross square 2m d2 psi x dx2 is equal to E psi. All right, so the automatically the Ux part becomes 0, or we can rearrange this part to write like this, because we can take this part here, so minus E psi is equal to 0 and then multiply by the positive sign and by 2m h cross we can write d2 square psi x dx2 plus 2me divided by h cross square psi x is equal to 0. All right, so this now becomes a perfect equation for a particle moving in one dimension and the particle is completely free. So the particle actually, this is the x direction. Okay, so this is towards negative infinity and this is towards positive infinity. So now the particle can move anywhere. It is free to move anywhere in one dimension between minus infinity to plus infinity, and the particle does not have any restraining force working on it. So this is called the equation, the Schrodinger equation for a free particle. All right, and you see we have eliminated Ux, so that means the Hamiltonian operator is only the kinetic energy operator. So the Hamiltonian operator is only the kinetic energy operator. All right, so that means H is represented by p square x by 2m. This is exactly what this is. All right, this one. Of course we have rearranged that equation. All right, so now this is the lesson for us. So we have now found this. Question is, can you solve this? Okay, if you try to solve, what would be the value of psi x? All right, so don't worry, we will come back once again to deal this thing as an assignment problem later. So what we can do next is we put some restriction on it. Okay, and that makes a problem of a real life situation. What is the restriction of it? The restriction of it is now we do not restrain the particle by the potential energy, but we restrain the particle by a boundary. So what is that boundary? So we have arbitrarily put a boundary over here and we define our reference like this. So here x is equal to 0 and here x is equal to a. So my entire length is called a. All right, and this is a boundary. So boundary at the left hand side and boundary at the right hand side. And of course this definition is completely arbitrary. You can put at the center position 0 and you can take that x as minus a and that x as positive a. It is up to you, doesn't matter. But for the time being my particle is now confined within this limit length a. All right, now what happens is the particle is free to move within this area. All right, absolutely. And within this area its potential energy ux is equal to 0. All right, area means this is the line because the particle is moving in only one dimension. But the moment the particle comes to this wall, its potential energy, all right, its potential energy becomes very high. All right, its potential energy actually becomes infinity, okay, at the wall. All right, so that means the particle cannot approach the walls, means it cannot get into the walls, so it should stay away from this and it is confined. That means the particle can never come out or jump the boundary because the potential energy is so high, infinite. And of course the wave function psi x, the wave function psi x, here outside the boundary is 0 and here also the outside of the boundary is 0. So therefore we can write that the psi at x is equal to 0 is 0 and the psi at x is equal to a is 0. All right, but definitely psi not equal to 0 when the value of x is greater than equal to 0 or smaller than equal to a. Sorry, it is it should be yeah. So so the value of x should be greater than 0 and less than a, then only psi would have a non-zero value. Other than that, at the two boundary walls psi should be 0, potential energy is infinite, okay, and the particle is ready to move freely between the two boundaries as long as it doesn't touch the two walls. Now the problem like this is called a free particle, okay, confined in a one-dimensional box. So we can think about it as a box, although by the word box in our mind we have a conventional three-dimensional picture, but now we can think about that this is a one-dimensional box. So a free particle, so interesting part is the word free. The moment you write free, that means ux is 0. So a free particle confined means it is confined by two boundaries, confined in a one-dimensional box. So practical example, so you have heard about this conjugated system or read about this conjugated system in chemistry. All right, so here you see the pi electrons can resonate. Okay, so here we can have a delta negative charge and here we have a delta positive charge. So we can think about that this system is a particle means electron confined in a one-dimensional box. So electron can readily move from this end to this end anywhere and supposedly in one dimension, and it is confined here. So let's see whether this kind of system can be defined by this and whether we can solve the energy of it. So we will try to see that. So the question is, now since we know this equation and we know the boundary conditions, right? So here these conditions are boundary conditions that you can easily recognize from your previous knowledge. So the question to you, can you solve the energy for a free particle confined in a one-dimensional box given this, the Schrodinger equation of the system, and given this is the boundary condition? An example is something like this, electron in a conjugated system. Okay, so can you do that? So we will see whether you can do that in the next lecture, that is lecture 12. So please keep on trying. Until then, goodbye.